Okay, here is a helper video for the assignment that I left you when you had a sub on Tuesday. So I said you could also use your graphing calculator to help you complete this. Okay, so first of all, you are moving at 8 miles per hour. Man, you're fast. You're going for 5 hours. How far have you traveled? Okay, 8 miles per hour means that you're going 8 miles every hour. Okay, for those of you who are unclear on what MPH means, you're going 8 miles every hour. So if I'm going for 5 hours, then I'm just going to do 8 times 5, which gives me a total of 40 miles. Okay, if you think about it with units, I know those of you who are in science, which is like everybody, it would be 8 miles per hour times 5 hours. The hours cancel, and you're left with 40 miles. All right. Graph this situation with a velocity graph. I want the velocity on my y-axis and the time down here. So I'm going 8 miles per hour. So when I first start moving, I'm going 8 miles per hour. An hour later, I'm still going 8 miles per hour. Hour later, still 8 miles per hour. I'm going 8 miles per hour the whole time. So there it is. I'm going 8 miles per hour for 5 hours. So I have a constant velocity. Constant velocity, okay? So my v of t, another way of saying that, v of t is equal to 8. Okay, it's always 8. My velocity is always 8. Use a highlighter to shade and then find the area under the velocity curve, which is a line in this case, between 0 and 5 hours. So here's 0 up to 5. So I want to stop here. I'm going to grab a highlighter. Here we go. And I'm going to shade this in. And I want to find the area of this. Well, let's see. I could count every box, but that would take a long time. Instead, I have 1, 2, 3, 4, 5 columns that are 8 units high. So 5 times 8, which gives me, lo and behold, 40. Well, isn't that interesting? The area underneath the velocity curve is the same as the total distance that I've traveled. Oh. So that is like a little aha moment. I should have asked you a question right there. I should have said, what do you notice about the answer to the area and the answer to how far you've traveled? They are the same. Okay, the area underneath the velocity curve is equal to your total distance traveled. Okay, so you've traveled the same as the area underneath the velocity curve. All right, evaluate the following integral and explain how it relates to the above situation. Okay, so I have the integral of 8. So if I integrate that, that gives me 8x. And that's going to go from 0 to 5. So how is that related to this? Well, they both have an 8. Okay, so this is like taking my velocity curve and integrating it. So when I integrate velocity, I get displacement or position. Okay, this is my displacement or position function. Because the derivative of the position function is the velocity, okay? So we call this displacement. I believe displacement is what they use in physics, so we'll go with displacement. Sometimes in calculus we call it position, okay? But it's displacement or position in relation to something is basically the same thing. All right, so now I'm going to evaluate that. So I'm going to do 8 times 5 minus 8 times 0, and I get 40. So if I integrate the velocity function on my time interval, 0 to 5, I also get the same answer. That is that same distance. So I get my distance. Okay, area under the curve, I can get it by making an integral of that function, and since this is a velocity, it gives me the total distance traveled in that time period. All right. Next question. The particle is accelerating at a constant rate of 2 meters per second squared. If at time 0 the particle is moving 1 meter per second, okay, time 0 it's moving 1 meter per second, graph the velocity function on the graph. Okay, it's going to accelerate. It's going to get faster every 2 meters per second every second. That's what this means. So 1 second later I'm going 2 meters per second faster than I was before. Every second later, I'm going 2 meters per second faster than the second before. So I can take that across. So here's my velocity. My velocity is increasing. It's not staying the same. I'm getting faster and faster and faster. I'm getting 2 meters per second faster every second That's what the acceleration is telling me. So I've graphed it. Now write an equation for that. Okay, y equals, my slope here is up 2 over 1, so 2x, and my y-intercept is 1. Now solve the indefinite integral. Hey, notice that, 2, that's the same as my acceleration. If I integrate acceleration, I'm going to get velocity, because the derivative of velocity is acceleration. So by taking the indefinite integral right here, I'm going to get the velocity function. So if I integrate this, I'm going to get 2x plus c. Because notice it's indefinite, so I got to write my plus c. Now explain why c equals 1. Well, it equals 1 in order to match the starting position. Okay, we have a starting position for the velocity. It's starting at 1 meter per second. So we have a starting velocity, I should have said, not position. We have a starting velocity of 1. So my c has to be 1 to match the original function. C equals 1. And how is the integral related to the problem above? Okay, this is 2 was my acceleration. So acceleration is the derivative of velocity. How fast are you? Okay, acceleration is the derivative of velocity. So when you integrate acceleration, you get velocity. C has to be 1. To match the velocity function. So the question might arise, well, why didn't that end up being a 1? Why do we have to force it to be a 1? Because think about it. If you take the derivative of 2x plus 1, the derivative of 2x plus 1 is just 2. The 1 disappears. So that's why we have the plus c, because we don't know what the original function was. But in this case, we do know what the original function was. We knew the original velocity function was 2x plus 1. Therefore, if I solve my indefinite integral, in order for this to be related to this graph, the c would be a 1. All right, highlight and find the area under the curve from time 0 to 3 seconds. Okay, we're going to 3 seconds. So I want to find this area. Okay, a couple ways I could do this. I noticed that if I cut it right here, I have a triangle. I've got 3 units here, 1, 2, 3, and then I have the area of this triangle. So I have 3 by 1, 2, 3, 4, 5, 6. So 1/2 3 times 6. Can you see that? Am I off the bottom? No, there I am. 1/2 3 times 6 plus this additional little rectangle here, which has an area of 3. So 1/2 3 times 6, 3 times 6 is 18, divided by 2 is 9, 9 plus 3 is equal to 12. So that would be 12, we're just talking about the area, it's units squared. Evaluate the following integrals. So notice here, this is my velocity function. So my velocity function, if I find the area under my velocity function, what's that going to give me? Total distance. Okay, so this is actually my total distance. Since this is distance, the area under a velocity curve is distance. Since this is distance, I'm actually going to say this is 12 meters. The distance is actually 12 meters. All right, so let's see what happens if I integrate the velocity function by hand. This would be x squared times 1/2 times 2 plus 1x. And then I need to integrate it from 0 to 3. Okay, 2 times 1/2 is just, I should have written this over here, I'm running out of room. This just gives me x squared plus x from 0 to 3. I'm going to substitute in my 3. 3 squared plus 3 minus 0 squared plus 0. Okay, that's all just 0. 3 squared is 9. 9 plus 3, oh, that was familiar, it gives me 12. So if I integrate the velocity function on my time interval, I'm going to get my total distance. So that would be 12 meters. All right. Okay, so I hope we're starting to see what's going on here. Acceleration velocity, so I can do the antiderivative of acceleration to get velocity. And then if I integrate the velocity function, I can get the total distance. That has to do with my displacement. Okay, explain why the answer to F is, oh, here's that question. Explain why the answer to F is the total distance traveled by the particle in 3 seconds. Okay, you explain that. I'm not going to write it down. Write down and sketch the possible displacement function. Let c equal 0 and find its value when x equals 3. Okay, so if I want the displacement function, or the position function, if I want that, and by the way, in IB, they often refer to it as S. S of t is the displacement function. Sometimes they use P of t, but oftentimes they use S of t. So S of t is what they use. Don't ask me why. For velocity, where's velocity? Velocity, they use F of t. Okay, velocity. And for acceleration, they use A of t. Okay, so A of t is acceleration, V of t is velocity, and then for some darn reason, S of t is displacement or position. I think I've also seen it as P of t. I've never seen it as D of t, though. Okay, let's see. Write down and sketch the possible. So I'll let you do that, because what do you have to do here? Now you need to take the antiderivative of the velocity function. Oh, we already did that. Oh, that's why it says write down. You actually already did this, so go back and find it. What would be your displacement function? You already did it. That's why it says write down. But then you have to find its value when x equals 3. And notice it says let c equals 0. Oh, so where would that be? All right, next question. So I'll let you try and finish that up. Next question. A car is traveling at 20 meters per second, which is about 45 miles per hour, just so you know. At time 0, okay, so we're starting at 20 meters per second. Here's my velocity. So at time 0, we're moving at 20 meters per second. The car brakes at a constant rate until it is stopped 6 seconds later. So at 6 seconds, its velocity is stopped. It's 0. And it's going to be decreasing at a constant rate. Okay, its velocity is going to decrease at a constant rate. So I'm just going to connect these. So I'm going to make a straight line. Find the acceleration function. Okay, so in order to find the acceleration function, I know that that is the derivative of the velocity function. So let's go ahead and find the velocity function first. And this is at a weird angle. So what would v of t be? V of t would be this equation of this line here. So I see I have a y-intercept of 20. And then what is my slope? My slope is 20 over 6. And it's negative. It's going downhill. Negative 20 over 6. T, right? Because my x, I don't know why there's an n there, sorry about that. This is t, okay, and this is my position, s. All right, so I can reduce that, so I get v of t is equal to negative 10/3 t plus 20. That's my velocity function. Okay, so find the acceleration function. So I just need the derivative of that. So a of t is equal to the derivative of v of t. So if I take the derivative of this over here, I would just get negative 10/3. That's all I would have. All right, write an integral to find the total distance traveled. So the total distance, again, is the area underneath the curve, underneath the velocity curve. So we could actually figure that out by finding the area of this triangle, or we could do it by writing an integral. Find the area under the curve on the graph and show, oh, so then that's the next question. Question D, find the area under the curve on the graph. Okay, so you're going to write an integral using the velocity function, and I'll help get you started. It's going to go from time 0 to when it stops. When does it stop? It stops at 6 seconds. So the integral is going to go from 0 to 6. And this is the function you're going to be integrating. Okay? I'll let you take it from there. And then you're going to figure out what's the area underneath here. Figure that out, and they should match. They should be the same. If they aren't the same, something went wrong. Okay? Okay, now something a little new. If the velocity changes sign, So in other words, you have a positive velocity and then it switches to being a negative velocity. That means there is a change in direction. Okay, so now this is an actual like IB question. Okay, the velocity, let's see, when finding total distance traveled, we need to find the distance traveled in both directions separately and then add them together. So you're going to see what that looks like here on this picture. And actually, you know what? I'm going to stop right now because I just noticed I've now caught up with the notes. Bam! These are the notes that I gave you in class today. Mr. Myers' class, if you're watching this, I'm going to hand this over to Mr. Myers to give to you on Thursday, but here it is if you want to see it right now. Okay, so here's the first little part, little note about distance traveled. And then here is problem number 4 from my packet. Okay, so it gives an explanation over here, and it gives the answer over on this side. Okay, so I will let the camera gaze at that for a second. There you go. All right, so I'm going to go ahead and let you do problem 4 by yourself. Is there any more? Oh, this should have said 5. And this should have said 6. Okay, so once you get to 5, explain everything you think you understand now about displacement, velocity, and acceleration. So I want you to be talking about, what do you know about the derivatives? Who is the derivative of whom? And integrals. When you integrate velocity, what do you get? When you integrate acceleration, what do you get? How do you calculate distance? Which one of these do you need to integrate in order to find total distance? What do you do if there's a change in direction? Okay, actually, I do kind of want to go back to this one. Actually, yeah, now that I think about it, let's talk about this for just a second. So I have a car passing a flag. Okay, so here's my flagpole. We're going to look at it like overhead. So the flagpole, if I'm looking at it like bird's eye view, I'm flying over it, looks just like a dot. I see a car passing the flag. It's modeled by, this is its velocity. So the initial speed of the car at time 0, well, I change t to a 0 and I get my initial velocity. So, okay, let me see. I'm trying to think, what is this? Maybe not. Actually, I think I'll just let you work through this. Yeah, this one's not so interesting. Okay, so what is happening, though, is when, you know how I said that when the velocity changes sign, that means there's a change in direction? You can see that on the graph here. This is the velocity. It's positive velocity, and then here, it's the velocity is 0, and then the velocity becomes negative. So what's happening is the car, it has gone some distance, like away from the flagpole, and then it's turning around and coming back towards it. Okay, so we've got this velocity, and it's going perhaps away from the flagpole, then it's turning around and coming back towards it. So again, if I were to put the flagpole, so we could say that the car from 0 to 4.25 seconds is going away, and then at 4.2 seconds, it starts coming back again. So if I want the total distance, I need to know how far is it from here to here, and this is at 4.25 seconds. What's that distance? I need to know that distance. And then I also need to know this distance. And you can kind of see this is the distance from 0 to 4.25, and this is the total distance from 4.25 to 5. And the reason why it's below the x-axis is because the car has turned around and is coming back the other way. So we need to figure out this distance, which is this area, and we need to figure out this distance, which is this area. So if I call that area 1, this would be the same as area 1, and if I call this area 2, this distance would be the same as area 2. And then we have to add them together to get that total distance. So work your way through that example by looking at this, and this is what we're talking about, a change of direction. So perhaps I'm going away from the flagpole, and then I turn away and I start coming back towards it. Because the speed, in order to turn around, I have to reach a speed of 0 before I can return back. And that gives me a negative velocity, because velocity has to do with direction as well as how fast I'm going. All right. Good luck. Talk to you later. Bye.